Today, I would like to present to you a flagship concept for Venus. And this is a collaboration between Pat Beecham at JPL and I. And I must say that the combination of a scientist and technologist working together, both with similar senses of humor, I think has been one of the enabling things about this study. And we are helped by Richard Lynch at Goddard Space Flight Center and his team. The concept study team has been, the science team has really been a pleasure to work with, and one of the best parts about doing this. The science team members that you see here have some recognizable Venusians, but Pat and I also wanted to pick people who didn't work on Venus as their sole occupation, who were maybe Venus curious, as it were. Such that they would have a different set of eyes and think about processes a little differently and help us see Venus in a good way and get new information. So this science team has been working together over the last year, again with Goddard, Richard Lynch at Goddard, Michael Motto there, and Adriana Ocampo has been our NASA headquarters liaison, and she has been advocating for Venus for decades, as well as identifying new talent and good talented people. So we've also been informed by a host of generous colleagues who have volunteered many, many hours of their time to talk about their research and instruments and their thoughts. And to them, we owe a great deal of thanks. A flagship mission, in our mind, allows you to do in situ work at a planet. And at Venus, the challenge is that it's hot and it's cloudy. And I don't need to be flippant, but the reason I'm bringing this up is because we have this perception that there is a perception it's hard to get to Venus. It's hard to get to the surface of Venus. That is true. But yet we've done it. And we did it in the 70s and we did it in the 80s. And it's these pioneering missions that have set the stage for the questions that we want to continue to address with new knowledge, better instrumentation in a flagship. So, for example, Pioneer Venus, 1978. What were you doing in 1978? Well, we launched multi-probes, well-instrumented multiple probes into the atmosphere of Venus to measure the composition and dynamics. In 1985, the Soviets launched an incredibly ambitious mission, the Vega Missions, in a cartoon form here. These missions went to Venus. They released 2 balloons that lasted about 46 hours, 2 landers that measured chemistry at the surface, and then they flew off to rendezvous with a Halley's Comet in 1986. Just incredible, just incredible. And these Vega landers, plus their cousins, the Venera landers, are the missions that have gotten us the incredibly important rock chemistry that we need to interpret planetary history. Imagine, so we have 7 measurements from these landers of various elements, not a complete set. But imagine that you took 7 random rocks from the surface of the Earth and then analyzed them and tried to put together a story for Venus. For the Earth, the history of the Earth. That's what we have for Venus, and is one of the reasons why it's so critical that we get data from places that we understand better now because of the context allowed by the renaissance of orbital missions. Of course, we have Magellan in the 80s and 90s, did radar mapping, and more recently, the atmospheric measurements provided by Venus Express, and currently by Akatsuki, who is still going along and collecting incredible data about the upper atmosphere and the cloud tops of Venus. So Magellan, the global map provided by Magellan has been our fundamental advance in putting these in situ data in context and understanding the history of this planet. And what you see here is a topographic map of the planet Venus. And we know from Magellan that the majority of the Venus surface is comprised of volcanic plains, volcanoes upon lava flows upon volcanoes. These plains are inferred to be basalt from the measurement of the landers and from morphology. And to everyone's surprise, the crater age, average crater age of the surface of the planet is about 500 million years, give or take. So it's telling us that Venus was volcanically active, but the way that it resurfaces itself is different than the way the Earth does, in a way that we still don't quite understand. Massive lava flows, sort of in the last billion years. Is it different? What is the difference? How is Venus recycling its heat? It's another M member of a terrestrial planet system. But in issue, one of the things that having a sort of modern resurfacing, lava resurfacing does is it obscures the oldest rocks on the planet. And just like Mars, we know from the D to H values for the Venus atmosphere that Venus has lost a lot of water in its history. And so just like Mars, we want to go to the rocks that will have a record of that history. The Magellan data through the basic geologic mapping has shown us that that history is most likely preserved in Tessera terrain. These are highly deformed, most often high-standing areas that are older than the plains, and they experienced an extinct a history that is extinct. Their deformation is different, and they came from a time before the plains. They are perhaps our only hope of finding rocks for the first 80% of the history of the planet. So now we know where to go. And in concert with this, the Venus community has been doing a lot of very good thinking and beautiful mission proposals, I have to say. Since Magellan, there have been details about upper atmospheric dynamics and composition from Venus Express and Akatsuki, plus a series of observations I'm going to focus on for which those payloads were not optimized. And what I'm talking about specifically is the 1 micron emissivity data from the Virtus instrument on Venus Express, which sees through the windows in the Venus, through atmospheric windows in the Venus clouds. So you're getting an emissivity signal from the surface. And in that emissivity, we can infer something about composition and temperature. And from those data, we've learned a couple things. We've learned that Venus may be erupting lava right now. We see differences in the amount of weathering, that the color differences in the Venus rocks correspond to differences in weathering that may indicate that some volcanoes are very young and less weathered. We see from VEX also transient thermal anomalies on the surface associated with rift zones that might indicate a lava flows and lava activity happening over days in the last couple of years. On the flip side, we also have been able to see different characteristics of the older crust, the Tessera, in that the emissivity characteristics are consistent with a non-basaltic composition, a composition that is more silica-rich, felsic, like the continents on the Earth. And if they are formed by the continents on the Earth, to make the continents on the Earth, you need melting of hydrous mantle and lower crust. You have to have a lot of water, and you have to have a mechanism to recycle that water into to be melted and produce felsic lithologies. So if these rocks were indeed felsic, that would be a record, again, of an ancient, extinct, and more water-rich environment. Independently, people have taken the Vega profiles and squeezed the life out of them to produce new GCM models that show that Venus may have had clement conditions and been stable for liquid water, stable on the surface for billions of years, which is a revolution in our way of thinking and forces us to think about Venus as a once habitable planet. And coincidentally, there has been a resurrection of an old hypothesis advocated by Morowitz and Sagan in 1967, that the realization that the Venus clouds are clement, they have things that microbes like to eat, and that the clouds themselves may be an extant habitable zone on Venus. So all of this is summarized in this graphic, which I have taken from a Scientific American article that was published last year by Darby Dyer. On the right, what you see are 4 stratigraphic columns for the 4 inner planets. If you just focus on the red and the blue, you'll see that the red is the record of volcanic activity. So old is at the top, young is at the bottom. We all know that size dictates how much heat you have, and so Mercury and Mars have sort of petered out. Venus, just by virtue of its radius, should have a similar, be similarly geologically active, have enough, same amount of heat as the Earth. And the new GCM models have revised this line of the presence of liquid water such that liquid water may have persisted on Venus for longer than Mars, actually billions of years. And I like to think about this and visualize this with the graphic in the upper left. If you came to the solar system 3 billion years ago, you would see 3 terrestrial planets, each of which had an ocean, and at least one of which, on at least one of which life had developed. The Tessera, which you see in the lower left, you can see the emissivity data. The blue is different than the red. It's low emissivity tessera, which are different than the basaltic plains. The age of these rocks overlaps with the last part of the modeled presence of liquid water. And so even the crater age of these surfaces may mean that they come from an era that was more water rich, to say nothing of the actual rock ages in the tessera, for which we have no constraint. And finally, I'd like to emphasize that we live in a time when I can tell my sons, when they look at the stars, that every star has planets around it, and we are desperate to find other Earths. Many of these Earth-sized planets will not be like Earth. They may be like Venus or something else. But as Steve Kane, who's on our science team, likes to say, Venus is the only exoplanet we will ever touch. And that is something. So the goal of the Venus flagship is the following. It's a mission to assess the habitability of Venus. We want to understand the history of volatiles and liquid water on Venus and determine if Venus is habitable, understand the composition and climatological history of the surface of Venus, and the present-day couplings between the surface and atmosphere, which are so critical, and understand the geologic history of Venus and whether Venus is geologically active today. And I just want to take a moment to talk about our approach. We wanted to define, of course, a scientifically compelling flagship mission, but that was affordable and doable in the next decade. It has to be done in the next decade. And to do this, we chose a single launch vehicle, and we chose instruments that were proven instruments that required minimal technology development. For example, we set a goal for entry loads to be 50 Gs or less to ensure that we didn't have to rely on instruments of the future, that we could use the complement of instruments today, in development today, or flown today. We wanted to land in Tessera and survive there for 4 to 8 hours, 4 to 8 hours. And we have accommodated a technology demonstration and a student-led instrument. Over this year, we have all of you on this telecon have drawn from extensive past studies, canvassed the community for input, had many, many, many telecons, and had tens of scientists and engineers provide their expertise. We folded it into an STM that we have helped use to help Goddard direct this study. The flagship mission, the key to the flagship really is the synergy. It's the ability to measure phenomena at different places in the Venus system at different times, simultaneously for long durations. And the flagship consists of several elements: a large orbiter and 2 small sats, which support the in situ, they do their science and they support the in situ assets. We were able to design a lander that can survive on the surface for 7 hours after 1 hour of descent. An aerobot that is variable altitude balloon and lasts for 60 plus days in the Venus clouds, plus LISSI, the long-lived surface lander, which can, due to high temperature electronics, survive on the surface of Venus for 60 plus days. This concept is the result. We've had 2 Goddard runs, one in person and one virtually for 2 weeks, where I sat in this very chair for many, many hours. We have 6 objectives. The first, determine if Venus wants hosted liquid water at the surface. And I'm going to introduce the measurements we want to make and then talk about the instrumentation that we use to do it. So to determine whether Venus hosted liquid water, we want to measure the global composition as derived from near-infrared emissivity and look for geomorphology of a water-rich past with higher resolution image data. We want to measure the noble gases and their isotopes through below the clouds all the way to the surface, on the surface, and combine that with mineralogy, chemistry, and surface images of Tessera material, the material where we think the water is most likely to have interacted. And to add to that, the history of volatiles is not complete without an understanding of where they're going and at what rate and who's leaving. And the small sats are designed to measure from 2 vantage points the escape of water and oxygen and how that depends on solar wind conditions, as well as magnetic fields. Objective 2 is to identify and characterize the origins and reservoirs of volatiles today. This is measuring the composition of volatiles through the atmosphere, in the cloud, through the atmosphere with the probe, in the cloud with the balloon, in the upper atmosphere through sounding with the orbiter and small sats, and also looking at the near surface chemistry and dynamics with all of these assets. All of these assets are measuring composition and wind, speed, direction over time in each of these places and integrating them together. Objective 3 is to place constraints on whether there are habitable environments on Venus today and search for organic materials. To do this, the balloon will measure the environment and the weather in the cloud over 60 days through a variety of latitudes, measure the size, shape of aerosols and cloud particles, and use fluorescence to look for the signature of biomolecules in the droplets that are collected. Objective 4, constrain the composition of surface and chemical markers of past and present climate. These are a set of instruments to look at weathering. What is the nature of surface weathering? This comes from near-infrared emissivity, looking on the ground at the mineralogy and chemistry, and also to characterize the near-surface environment. What is the atmosphere doing? What is the coupling between the surface and the atmosphere? And do we have a record of climates that in the rocks that are not present, that are in disequilibrium with the pressure, with the atmosphere today? Wouldn't that be wonderful? Number 5, determine if Venus showed evidence of a current or past plate tectonic regime, global composition and imaging, gravity, mineralogy of Tessera terrain. And then on a balloon is a wonderful platform to measure magnetic remnant magnetism, look for and characterize remnant magnetism. And so there's a magnetometer on a balloon to try to look for that. And lastly, we want to determine whether Venus is tectonically and volcanically active today. This can be done by looking for change detection and imagery, thermal anomalies through emissivity, infrared emissivity, and transient changes in the composition of the atmosphere, in the surface and the cloud, and even in the cloud particles themselves. Volcanic ash, for example, increases in SO2. These are things that may mark transient events. And in addition, we would like to use infrasound to measure seismicity over the lifetime of the balloon. The mission, we investigated several key trades, and I will review them here. So we were able to fit everything in a Falcon Heavy with a 5-meter fairing in a single launch. We spent a lot of time. It's really hard to carry assets to a planet, drop them off, support them, and then go on to do science with the orbiting asset. And we spent a lot of time negotiating and trying to make all of those things happen together and well and efficiently, so that it could be done. For the lander, we considered trade-offs between sample ingestion and interrogating external samples with Raman libs, the thermal environment, lander legs, hazard avoidance, which we baselined. We have a variable altitude balloon, which we also baselined after consideration. And for the orbiter and small sats, again, it's a balance between science and comm that has been very tricky. And also we investigated whether or not it was necessary or feasible to map the Tessera landing sites with the orbiter prior to deploying the lander, and decided that it was not very feasible. So you can read all that in the report. Our nominal launch is in 2031. The small sats will go to Venus and do their thing. They will insert into Venus orbit. The orbiter will, the carrier will fly by Venus and then return to Venus a couple years later to firstly deploy the aerobot and balloon, support that balloon with the orbiter and small sats. And then about a year later, half a year later, drop the lander, support the lander operations, and then the orbiter will aerobrake down into a circular orbit and collect surface science and atmospheric science for 4 more years. End of mission is 2038. The lander science is familiar to many of us because it is close to, it has the same similar instruments to Da Vinci, and there's no secret here. This is what you want to measure. This is what you need to measure. A mass spectrometer, tunable laser spectrometer to do noble gases, trace gases, and their isotopes. Because this is in the lander itself, it's designed to survive the surface, land on the surface, and make these measurements on the surface during the first hour or so of the landing campaign. I have a snarky little quote here about what we know about the lower atmosphere, but it's kind of true. And this is the way to interrogate it, and this is what has to be done. The landing sites will be Tessera. The Tessera here are shown in yellow, and we considered several landing sites, but picked a near equatorial landing site in Western Avda, and so we engineered to this location. And one of the problems with Tessera terrain is that it's rough, and it's rough on several different scales, some of which we know better than others. So what you're our stereogrammetry data gives us about a kilometer resolution sense of slopes. And what you're seeing here, this is the Western Avda, this is the landing ellipse for the lander, and these are the slopes that we can calculate at the 1 kilometer scale for this landing ellipse, and they're pretty benign. They're not too bad at this scale, but we don't see, or we don't have knowledge of potentially unevenness in the surface, or what the surface materials are like, or if they're very rare but very dangerous, fault scarps, for example. So these are the challenges, and we propose several solutions. One is somebody in the Venus community, we really, I think, need to make some comprehensive slope map analyses and interrogate the radar data and Arecibo data, as Bruce Campbell's been doing, to understand the nature of mantling materials and rock sizes in the Tessera to help enable Venus Tessera landing. We also implemented hazard avoidance, real-time processing of descent images and LiDAR, similar to what Carolyn was saying about Mercury. And but unlike Mercury, we can use fans because we're under a Venus ocean to redirect the lander to avoid potentially steep slopes. The lander is designed to tolerate 30 degrees. And we also have redundant instrumentation. And this redundant instrumentation is not just to get more data, it's also an operational advantage. And the reason for this redundancy is the brainchild of Alison Santos. We had endless discussions about, do we ingest rocks? Do we use ramen libs? Do we ingest rocks? No. And she said, why don't we do both? And it was like, so we are. That's what we're doing. And it allows you to do incredible amounts of science, actually, and gives you more operational flexibility. The plan is to ingest the samples into the lander. They will be delivered to X-ray fluorescence, and then which is VXL, and then dropped into a hopper to be analyzed for mineralogy by ChemMinV. So these will allow us to have samples that are less weathered. And then Allison and Darby Dyers talked about this too. So, the Raman Libs is an example of mobility at Venus. It allows you to shoot a laser at multiple targets over time and interrogate tens or hundreds of rocks, and look at their weathering. In addition to that, Becca is the neutron gamma ray instrument that can interrogate a volume of soil underneath the lander. So all of this is the field of view of the cameras is all the way around 360 degrees. For the panoramic cameras, 4 filters. The Raman Libs has a window off the side. This is designed to show what Becca will see. And then the descent imager is designed, it has a 90-degree field of view and it's off kilter such that it can see not only descent, but the drill site before and after the samples are acquired. This image, I'll just talk you through this. This is the surface timeline. I just want to show, this is minutes on the bottom. This is the 7-hour nominal lifetime. This is the temperature of the interior over the 7 hours. And what you see here is in colors, these are the atmospheric measurements that were taken on descent and will be continued to be taken throughout the first part of the landed mission. We have the ingestion and sampling of the rocks through the drill at the beginning. And these are all placed at the beginning to take advantage of the fact that the orbiter can only see the lander for about 90 minutes at the start of the landed mission. And so we critically rely on the small sats to return the other data over the 8 hours. And in fact, it wasn't the thermal. The thermal was not as big as an issue for long life as the comm was with a single orbit, a single launch. So the small sats come in, these 2 small sats, and allow Becca to integrate for 1.5+ hours, collect all of its wonderful data. And for Raman Libs to interrogate, just think of how many rocks you could look at in 7 hours on the surface of Venus. LISSI is on its own. It talks to the orbiter by itself, and so it would last for its 60 days plus. We have a wonderful aerobot. Colin Wilson has been taking the lead on this, and he has convinced me of the importance of understanding the clouds as the interface between the upper atmosphere, about we know something, and the lower atmosphere, about which we know less, as well as the fact that this is potentially that the habitable zone of Venus, if it is indeed habitable. We will measure the clouds using a suite of instruments, aerosol mass spectrometer and nephelometer, to ingest materials that will then be analyzed by fluorimeter to look for fluorescing biomolecules. A sophisticated meteorology suite, and surface science. an infrasound pressure sensor to take advantage of the fact that the dense Venus atmosphere will transmit seismic signals above a certain threshold, about 4 to 5 magnitude. Venus quakes can be detected from balloon just by listening. And Jennifer Jackson has been helping us with design this aspect of the mission. The balloon will be in orbit. We'll be making these measurements for 60 days. And in that time, we expect there to be tens of earthquakes of that magnitude or higher that might be detectable by this method. Also, the magnetometer will be able to measure the float above the surface of Venus from the equator where it's inserted to whichever pole the balloon floats to, and measure the magnetism, the magnetic flux from the surface over half of the planet via balloon. The Aerobot flight plan is to start out by hanging out at a single altitude and getting ourselves together, dwell at 56 kilometers. There will be 12 circumnavigations of Venus over the nominal lifetime, and then do variable altitude surveys to study the very different, the cloud tops. There's quite a difference between the cloud tops, the environment of the cloud tops, and the cloud bottoms in terms of the droplets, the temperatures, the chemistry perhaps, and do this at different times of day over the lifetime of the balloon and night. The orbiter, I'm aware of my time, everybody. The orbiter is, the major elements are a radar, high resolution radar, a near infrared imager, electrostatic analyzer and magnetometer to complement the data that is being collected by the small sats at the same time, and submeter, sounder, and radio occultation to look at winds and density profiles of the upper atmosphere. The radar is, as I think Jorn Halbert said at one backside, you take a camera to Mars, radar is the camera for Venus. It's not really optional to see the morphology. This is the wavelength we have to use. And in a moment, I'll talk about how this radar may dovetail with other radars that might be flown, hopefully, before this flagship mission. After lander release, I said it will aerobrake to a mapping orbit. The small sats, Shannon Curry has done an incredible job at helping us think through and providing us the design for these small sats. They'll be in 2 elliptical orbits with periapsis in the northern and southern hemispheres, and they will measure portions of the exosphere of Venus that have not been previously measured, measure it better, and measure it over a longer period of time. Again, this is where the ions are going. This is where the water is going. And to measure this simultaneously with Venus, what's in the Venus clouds, what's in the Venus, and also geologic activity and solar activity is essential. A communications diagram here. All of the orbiting elements will communicate by S-band to the lander and the balloon. The LISSI has its own UHF, talks directly to the big orbiter, and then the orbiter and small sats will communicate via X-band and Ka-band down for the orbiter to DSN on Earth. So just a couple slides here at the end. The flagship does not obviate any of these missions. In particular, I wanted to speak to the 3 that are in contention. Veritas and Da Vinci, of course, are in Discovery Phase A, and Vision is being considered as an ESA M5 candidate. And these are not in competition in terms of science. Veritas, with its global mapping and topography, incredible topography, would be a pathfinder for any landed mission. Lander site selection would be highly enabled. Risk would be reduced by having higher resolution maps of the entire surface. And the Venus flagship could add high resolution SAR targets to help and add to the limited high resolution SAR targets that would be taken by either Veritas or Envision. You can't, it's like Prism, I mean, like a high rise, you can't image the entire planet at high res. So there's a complementarity there. A possible deep scope might be that near infrared imager may not be needed several times on several missions, but Veritas is necessary for the global mapping. Da Vinci would provide another descent profile at another location. The flagship itself is planning to do surface science with the same instruments for a couple of hours. One could argue that noble gas measurements are not necessary because noble gases should be the same everywhere on Venus, but maybe they're not. You can't tell unless you measure them again. Envision is an interesting case because the launch date is similar to the flagship mission, and so one should consider that if the two missions were operating concurrently, that Envision could provide SAR and near-infrared support to meet the flagship objectives and thus release the flagship from having to carry those instruments if they were together in orbit. The Venera D lander, which is under study, will visit the plane, so it's a different set of science objectives. I'm going to summarize this slide by just saying that it's the synergy. It's the flagship is about the synergistic measurements in situ, multiple vantage points over time. And I've said it before. I've said it before, so I want to leave time for questions. But it's this long-term chemistry on the surface, 7 hours on the surface, long-term surface monitoring, long life in the clouds, measuring the ions coming out off of the top of the atmosphere, and this box of firsts are things that the flagship would do uniquely if it were to fly. The ones that are in sort of grayish here are things that would be first if nothing else preceded it. But certainly Da Vinci and Veritas would make these measurements. I hope they do make these measurements before a flagship mission. But a flagship is still essential for this integrated look at the Venus system. And the application to Venus is also beyond our own solar system. The verbiage here is the verbiage from from heliophysics and exoplanet strategy reports. Exoplanets wants to know, how do we find habitable planets? Heliophysics wants to know how Earth, planets, and the heliosphere interact. And Shannon Curry has taught me now that guess what? Between Earth and the sun is Venus. And we want to understand what the sun is doing to the Venus atmosphere. And lastly, the four major questions of solar system science: how did life begin and evolve? The solar system evolution, sun's family originate, and the characteristics of the planets are all answered by Venus. So we hope that a flagship will be flown to provide understanding of Earth-sized habitable worlds. And I am done. So thank you for your attention.
Thank you.
Thank you so much, Marty.
Martha.
You're welcome.
Oh, hi. See, now you have two headquarters moderators. I do apologize. All of a sudden, Ring Central kicked me out. My computer turned off.
Oh, goodness.
So, no, but I was able to hear all of your presentation. Thank you so much. And we do have a few questions. Some of them already have been answered by your team.
Okay.
But I'm going to go ahead and repeat them so you have a chance to say I agree.
Okay.
First question by Kirby Runyon. Could your architecture take advantage of crewed Venus flybys during, for example, a crewed Mars opposition class mission, which requires a Venus flyby? And the answer from your teammate was, it depends on what the crewed mission could carry as payloads. So,
but all Venus flybys are excellent opportunities, as Adriana has been, the Vigasso program, excellent opportunities to do different aspects of science. And I think the more assets that we are able to design, the more opportunities we may have to take advantage of these types of flybys.
Great. And then a follow-up by Kirby saying, did I hear right that it is fans instead of landing thrusters on the lander? Cool.
Yes, and yes.
All right, let me see. Here's a question that I think your teammates have not seen yet. It's by G Driver and T Bays from Burbank, UK. Just wanted to say thank you for the last 2 days. The talks have been brilliant and very informative. Well, you're welcome. Sorry, that wasn't a question. Hailey Phillips from NASA Glenn. To those of you who worked on the Venus flagship study, well done. Thank you all for your hard work and great progress.
That's nice. Thank you.
Catherine Elder from JPL. Did you consider a seismometer and or a heat flow probe for the longer-lived lander?
Yeah, those are part of the SAVE concept, which was one of the PSCS3 studies, and it's a wonderful, which is wonderful, but it's not going to be ready likely in the time frame that we're considering, and it also requires deployment onto the surface. And so LISI, upon which SAVE is based, has the capability to serve as a technology demonstration and a pathfinder for a seismometer mission like SAVE. And it's simpler, and we don't have to develop the mechanisms to actually get it on the surface. We can just pop it on the top and bolt it on.
All right. Another question from James Haber from Purdue University. Did I hear correctly that landing sites to recon would be very limited? Wouldn't the rough terrain of the Tessera require at least some by the orbiter or at least the landing system, maybe terrain navigation like MSL?
Yes, yes. I didn't say that the orbiter would be able to collect some data prior to deploying the lander, perhaps not the exact landing site, but higher resolution data of some aspects of Tessera would help us extrapolate into other aspects, other portions of Tessera. But yes, I think I discussed that the hazard avoidance, we would like to take advantage of whatever we could do with the LiDAR imaging, actually, and descent imaging to autonomously move the lander.
And one last question by Jayadev Pradeep from Israel. Did you consider the possibility of incorporating the versatile method of solar occultation to study the upper atmosphere of Venus, as done in SPICAV Venus Express? Considering that the Nominal mission would have 3 spacecraft orbiting Venus, doesn't this open up exciting possibilities with regards to solar occultation studies?
Yes, it does. And I don't think we've considered that. We've talked about radio occultation, but I appreciate the idea, and yes, it does. I think there are many things that people can do with all of those assets at Venus. Thank you.
All right, let me check to see. Okay, another question by Avinash Das. Could you please explain how the balloon will be able to collect seismic data?
The science behind this leverages the fact that because the Venus atmosphere is so dense, that a wave generated by seismic shaking, seismic motion, will be transmitted up through the atmosphere, and you can hear those waves at infrasound wavelengths. So it's the density of the atmosphere that allows this to happen. This happens on Earth too, actually. We don't bother to look for it because why would you do that? But you can actually see the waves propagate all the way up to the upper atmosphere. And on Venus, the waves should be detectable by infrasound in the atmosphere itself, and also at the top of the atmosphere by dayglow, oxygen dayglow measurements. So it's leveraging this atmosphere that will be transmitting those seismic waves that we can detect by measuring the difference in pressure across across two pressure sensors, actually.